I now want to introduce the idea of vector spaces. So consider the vector v drawn below. So we can describe this vector in a different set of bases, as we'd have in a previous video. So in the basis I hat j hat, for instance, associated with x and y, can write v as I hat plus j hat. I could also write this in a alpha beta basis, where alpha is the vector here, beta is this vector, or written out, alpha is, say, I hat plus 3j hat, and beta is 2I hat. And if I write this vector in this basis, v is 1/3 alpha plus 1/3 beta. Now the important point here is that both of these are equivalent descriptions of the vector v. I can write the vector v in different bases, but it's still the same vector. Okay, so now consider something that's seemingly unrelated, namely the polynomial f of x is 6x squared minus 5x plus 2. Namely, I have 6 of the x squared minus 5 of the x and plus 2 of the constants. I can also write this polynomial in another way. I could write this polynomial as f of x is 4p2 of x minus 5p1 of x plus 4p0 of x, where these p's, p2, p1, and p0, p2 of x is the polynomial 1/2 3x squared minus 1, p1 of x is x, and p0 of x is 1. These are the so-called Legendre polynomials that you will probably see in different contexts. So I can equally write the polynomial in either of these two ways, and you can check that they're the same. Again, both of these descriptions are completely equivalent to each other. So the similarity between these leads us to the idea of a generalized idea of what we mean by a vector space. So a vector space doesn't just have to mean vectors in the traditional sense. So in particular, what we've shown here is that, what we're arguing, is that the set of all second-order polynomials is what we're calling a vector space, in that it behaves a lot like vectors normally would. In particular, any second-order polynomial is therefore a vector in the space of polynomials, all possible polynomials. So the vector f of x, or the polynomial f of x, which was 6x squared minus 5x plus 2, is a vector in the space of all possible polynomials. And it's a vector in the same sense that v was a vector in the space of two-dimensional vectors. Also, any vector, or in this case that's a polynomial, can be expressed as a linear combination. In this case, we saw it was a linear combination of, say, terms like a constant, an x, or an x squared. So we like to say then that one x and x squared is a basis for second-order polynomials. You can write any polynomial as a linear combination of these types of terms. Note that that's not the only basis. In particular, any vector, again, if this is a polynomial we're talking about, can be expressed as a linear combination in a different way. So it can be expressed as a linear combination of the Legendre polynomials, say p2 of x, p1 of x, and p0 of x. Because of this, we say that p2 of x, p1 of x, and p0 of x are also a basis. They're an alternative basis for second-order polynomials. Now, this generalized idea of a vector space seems like it's a little bit strange when applied to polynomials, but it has a lot of the properties that you would expect. And so what I want to talk about is some of the familiar properties and how they work in normal vectors, and then how they will work for our generalized vector space for second order polynomials. So for vectors, let's consider we had two vectors A and B here. And for second order polynomials, let's take two vectors in that space, f of x, which we'll write in terms of these Legendre polynomials, and g of x, also written in terms of this way. Okay, so I have vectors in both spaces. One of the properties of a vector space is the property of addition. If I take those two vectors, I can add them together and I get another vector. So in this case, I add a and b and I get 2i hat. If I add f of x and g of x, I get, again, another vector, which means I get another polynomial, second order polynomial. I can also do scalar multiplication. So in particular, I can take a number and multiply it by a vector, and it's still a vector. So in this case, I get 4i hat plus 4j hat for if I multiply 4 times a. I can take 4 times f of x, which that means I can distribute it through into my vector, and I get another polynomial, 8p2 of x minus 4p0 of x. Again, another polynomial, so I get another vector at the end of the day. Another property of a vector space is the idea of an inner product. I can take a dot product between a and b. So I dot a and b. And if I just multiply this out, I get terms that look like I hat plus dot I hat plus I hat dot j hat. And there's also a minus I hat dot j hat. And there's a minus j hat dot j hat term. Okay, so the I hat dot j hat terms are 0. I hat dot I hat is 1. Same thing for j hat and j hat. So this inner product is 0. For f of x and g of x, I write the inner product in this way with parentheses, but what am I going to define this as? Well, it turns out we could define an inner product for polynomials. We'll define it this way. It's the integral from -1 to 1 of the multiplication of the functions integrated dx. So note, we're just defining an inner product here for what we mean by the inner product between two functions in the space of polynomials. I want to point something kind of cute out. The integral from -1 to 1 of these Legendre polynomials multiplied by each other gives you 0 if those polynomials are different and 1 if they're the same. So for example, the integral of p1 times p1 from 0 to 1, or -1 to 1, excuse me, is just 1. So that's one of the reasons we use Legendre polynomials. So let's take the inner product between f of x and g of x. So again, it's the integral from -1 to 1 of f of x times g of x, written here in terms of Legendre polynomials, integrated dx. Okay, so there's a lot of terms here. I'm just going to write a few of them out. So one of the terms I get is p2 of x times p2 of x dx. I get another term that's the integral of p0 of x times p0 of x dx. I also get some cross terms. I get terms that look like 2 times the integral of, say, p2 of x and p1 of x dx, and many other terms that look like that. So the cross term here, p2 times p1, is 0 because of how Legendre polynomials work. And then the integrals for the p2s and the p0s each give me 1. All those other cross terms will actually end up giving me 0 as well. And so this inner product is 1 minus 1, or 0. So again, the inner product between f of x and g of x in this case is 0. So you might say that f of x and g of x are perpendicular, in the same sense that you would say a and b are perpendicular. Their inner product is 0. The last property I want to talk about is the magnitude, or the norm. So for normal vectors, we're used to taking the norm, or the magnitude of a vector, is you take the dot product of the vector with itself, and then take the square root. Well, it's going to work the same way for generalized vectors. So the norm is the inner product of the vector with itself, and take the square root. And we're just going to call this the norm in this case rather than the magnitude, so that we can keep those two ideas distinct. Of course, there's other properties of generalized vector spaces as well, and you should look them up. I'm not going to go through all of them right here, but you should look them up and see if they make sense for you for second-order polynomials. But that's the general idea of what we're doing with generalized vector spaces.